discussion about line reflections yesterday and their properties, and I claimed that what we would do today is discuss finite groups of isometries and classify them to be the two most familiar examples of groups that we've encountered so far, cyclic groups and dihedral groups. Those are really the only groups that we've very thoroughly investigated so far, which is on purpose, of course. So this theorem is called Leonardo's theorem. And you know what I just realized? I was so enthusiastic to start talking about this. I forgot that yesterday I said we would start with addressing questions that will help us review for the exam. If there's any questions about the practice exam. So I want to be true to my word. Let's take any questions.
And we'll still have questions tomorrow also, right?
And we'll still have questions tomorrow before the exam. Yes. So are there any pressing questions this moment? And don't forget, of course, you'll also have opportunity to ask questions in office hours this evening and office hours tomorrow morning before class. So hopefully between those 4 slots, we can get all the questions answered that anyone has. Okay, so Keenan asked for fall 2010, number 4. Okay, so let's see here. Okay. So, first, number 4, 2010, which asks us to find the center, find C, and theta for the following equation. Rho sub C comma theta is equal to rho sub 0 comma 0 comma 180 times rho sub 0 comma 4 comma 90. Okay, so we know theta right away, right? By the angle addition theorem. The product of 2 rotations, regardless of their center, adds the angles, right? Unless, of course, the sum of the angles is 0 degrees, then you get a translation, right? Okay, so angle addition theorem implies that theta is equal to 180 plus 90 or 207. Okay, so how do we find the center of this rotation?
Express it as reflections and then find the fixed point utopian option.
That's one way to go. Yeah. So in the solutions, what we have is, and that's exactly what they do in the solutions, actually. Yeah, it's just, we don't actually write out the reflections, we just write the lines, right? Okay, so just by looking at these reflections that were given as our factors, we know we can express this if we choose an arbitrary line. And again, if we want to make our lives easy, let's choose the x-axis. Especially that's a good choice because both these centers are on the x-axis. Okay? So, first, let L be x-axis. Okay, and then essentially what we're going to do is find the line M such that we have a rotation, a directed angle between L and M of 45 degrees, half of this angle measure, this directed angle.
What did tell for that? No, it's not me.
Yeah.
That's interesting.
Yeah. Yeah. Okay. So, right. Then we'll choose, and just to follow the notation that's in the solution that you all have, then we'll choose a line N, they call it, with directed angle measure from N to L, 45 degrees. Okay, so let's draw a picture here. Choosing my x-axis to be L, and then I want to choose an N which passes through the point 4, 0 that has directed angle measure 45 degrees from N to L. So let's say here's my point, 4, 0, and this is my line N. This is my directed angle measure, 45 degrees. Okay? And then, furthermore, we want to choose a line that goes through 0, 0, that has angle measure 90 degrees, directed angle measure from L to M, right? Because we'll eliminate the L's on the inside, right? Okay, so what's the best choice for that? Well, that's just the y-axis, right? Has an angle measure of 90 degrees, and it passes through the point 0, 0. Okay, so we'll let this be M. Okay? So, what is the new center? What is the center of this product?
The intersection.
It's where N and M intersect.
So that's to fix it.
Yeah, exactly, because it has to be fixed. Okay, so it has to lie on both lines. Okay? So this is our point C. So now, all we have to do is to determine the equations of lines N and M. Well, line M has equation x equals 0, right? You can just see that by looking at it. Now, how do we determine the equation of line N?
Use trig.
Yeah, so you can use, one way or another, you're going to use trigonometry, right? You can either draw a triangle, right, to determine that this has slope of 1. Or another thing you can do is look at this angle, right, which is 135, and take the inverse tangent of that, and that's your slope. Okay? So, let's just say to find slope, either draw a triangle, and use theorems about triangles, theorems, but which essentially amounts to, or you can just, or take the inverse tangent of the complementary angle of the directed angle.
Is the slope not just the tangent of that angle?
I'm sorry. Oh, you're right. Why am I saying inverse tangent?
Well, I mean, it's the tangent of the actual angle, isn't it?
So the tangent of 45
Would be
is
the
1.
slope.
Well, but the slope is -1, right?
Right, yeah.
So you have to take the angle that starts from the x-axis to get the correct slope, right? Because the slope is -1.
The magnitude should be right, though, right?
The magnitude is right.
Yeah.
The magnitude is right.
Okay.
But, you know,
Yeah.
this is like some basic thing about trigonometry.
Yeah.
Like, it's like, oh, if you want things to be correctly signed in the plane, you have to choose the right supplementary angle. Okay? So yeah, I'm sorry. Why do I keep saying inverse tangent? This is the tangent. Okay? So, the tangent of 135 degrees is 1. Okay? So, I'm sorry, -1. Jeez. And then we do the standard thing. We just solve for the y-intercept, knowing that the line n passes through the point 4, 0. Okay? Yeah. So, y equals -x plus b. And plug in the point 4, 0. And you do some arithmetic and find that b is equal to 4, right? Not very hard arithmetic. And as the equation, y equals -x plus 4. Okay, so really all this problem boils down to is remembering that you can construct lines m and n that intersect a common line, an arbitrary line L, right? And the easy thing to do is always to choose L. Well, L is through both points that your given rotations are about. Okay, so that's why we get to use the x-axis. Okay. Okay, so I hope that's satisfactory. Are there any other questions about the review exams, practice exams? Okay, if not, that's potentially great news. But again, there'll be plenty of opportunities to ask more questions. So let's talk about Leonardo's theorem.
This is Leonardo like Leonardo.
Da Vinci, yeah, right. So, okay, just a tiny piece of, oh, sorry. So Keenan also had a question about 3C. Also from 2010, I presume, yeah? Okay, so Keenan asks, how do we determine if an element of Dn is a rotation or a reflection? And the answer to that is, you know that there's there's two n elements to the group Dn, and there are n rotations, which are just the power of the rotational generator. Everything that has a factor of sigma in it after you simplify everything is a reflection. Right? That's just a counting argument. Right? There's 2n elements of dn, and then once you know that there's exactly n rotations, and that dn consists only of rotations and reflections, the other n elements must be reflections.
It means every odd element is a reflection.
That's right. All the even elements are all rotations, and all the odd elements are reflections. Okay? So yeah. The takeaway of all that, I mean, that's all. Those are all the facts that we proved. The takeaway is that any element of dn that has a factor of sigma in it when it's in simplest form is a reflection. Okay? Great. So I just wanted to say a little bit about some tiny piece of history here. So there was this physicist in the early half of the 20th century named Hermann Weyl. And you know, he's classically trained as a physicist, but through much of his career, he tried to develop a kind of analog of synthetic geometry for differential geometry, as it applied to physics in particular. Okay, so let me just say, in 1952, Hermann Weyl publishes a book called Symmetry. Okay, which is, for its day, it was something like a pop science book. It was meant to reach a broader audience than hardcore physicists or hardcore mathematicians at the time, just because it was kind of a cross-disciplinary thing. So why I bring this up is because this is kind of, in this book, was the first modern mention of, it kind of reminded people that in his lifetime, Da Vinci actually solved this problem of determining what a finite group of isometries must be. Okay? Obviously, he didn't have the language of isometries on hand, but his work made a rigorous count of what exactly the isometries of, what a finite group of isometries must be. Okay? And his motivation for this, so Da Vinci classified all finite groups of isometries for architectural purposes. Okay? So his angle of attack was to say, okay, given a building, where can I add chapels or, you know, niches that will not break the symmetry that already exists there? Okay? So I'm just telling you this because it's kind of interesting. And, you know, it points to yet another instance of, so remember at the very beginning of the term I told you that our goal is to get to the point where we describe and prove that there are exactly 17 types of patterns you can make for wallpaper or plain tilings, right? And that this was known to 15th century Moorish people in Spain, right? So this is yet another example of how historically disciplines of design have addressed formal mathematical results before it kind of precedes the language of mathematics that makes it easy to see or easy to manipulate. So just a testament to Da Vinci's genius. Okay, so we'll reproduce this result in modern language. Okay, so here's the theorem. And I've already told you what it says a couple times. A finite group of isometries is either cyclic or dihedral for some n. So it turns out, in a certain regard, even though we've only really talked about two types of groups, they're of great importance to our subject of study. Really kind of all we care about for the moment. Okay? So, let's prove this. Let's suppose G is a finite group of isometries. Well, right away, that allows us to characterize the group in a certain way. Namely, G cannot contain certain types of isometries. Why?
Because certain isometries generate infinite groups by default.
Yes, exactly. So this, because we're assuming G is finite, we know that G cannot contain either a translation or glide reflection. Since each of these types of isometries generate infinite cyclic groups. So certainly we couldn't have a finite group that has an infinite group as a subgroup, right? Okay. So G contains only rotations and reflections. Okay, so at this point, we'll break it into two cases. First, we'll assume, case one, we'll assume that G contains only rotations. And then we'll assume, after that, that G contains at least one reflection. Okay? So, case one. G contains only rotations. Okay. So, firstly, let's just suppose G is not equal to C1, the trivial group, right, containing just iota. Because that's an uninteresting case, right? That's fine. Okay, so then let's assume that rho sub A comma theta and rho sub B comma phi are both in our finite group G, where we're assuming that A is not equal to B. So we're assuming that G contains two rotations about different centers. Okay? So because of the axioms of a group, this tells us that the following is also an element of G. Okay, I take the inverse of rho sub b comma phi, the inverse of rho sub a comma theta, times rho sub b comma phi, rho sub a comma theta. Of course, what's the inverse of a rotation? I just make the angle negative, right? So I get rho sub b comma negative phi times rho sub a comma negative theta times rho sub b comma phi times rho sub a comma theta. So by the group laws, the axioms for a group, this product must also be in G, right? We have inverses and then closure. Now, what's wrong here? This is bad of me to say. Why is that? Let me ask you this. What theorem am I trying to get you
The
to
total
use?
sum angle here is 0,
Right?
which means it has to be a translation, which can't generate a finite group.
Right. Good. Okay, so let's write that out. Since negative phi minus theta plus phi plus theta is equal to 0, the angle addition theorem tells us the product in question is a translation which contradicts the finiteness of G. So in fact, A was equal to B, after all. Okay? So,
Only containing rotations, only about 1 point.
right, what we've shown so far is that if we contain only rotations, it can only be rotations around a single point. Okay, so, right. Good. So, let me claim the following. By what we know about angles, every element of G can be written in the form rho sub a comma phi with, of course, phi between and possibly equal to 0 and less less than 360. With phi greater than or equal to 0 and strictly less than 360. Okay. So then, let's set rho equal to rho sub a comma phi, where phi is the smallest possible value, positive value. In G. How do I know there is such a smallest?
It's finite.
Because it's finite. Yeah. Good. I mean, of course, remember that G ranges over, phi ranges over real numbers. So you could say like, oh, you can make phi as small as you want, but G only contains a finite number of elements. So there has to be at least one.
But then it has the limit MAP group, so.
Yeah.
So do you not find the smallest possible? I'm a little confused about that.
I'm sorry?
I'm a little confused about that. How could we not have like a smallest possible value if it's finite?
So, that is to say, we agree that we can write every element of G in the form of rho sub a comma phi for some phi
Alright.
between 0 and 360. And since there's only a finite number of possible phis, one of them has to be the least. We're just comparing
Okay,
them.
you're just saying there's a at least.
Yeah.
Okay, because it's fine.
It's not constructive in any way. I'm not telling you how to find the least. It's
Yeah.
just, we can say it exists.
Okay, there exists a very small fee, okay.
Yeah, or, well, not
It
even.
doesn't even have to be
It could be really big if it's some group, I guess.
for some.
If it's like C2,
Yeah.
right? That's as big as it can get. Unless it's C1 and then you have the identity.
That's the thing.
Well, C1 makes it go back to 0. So C2 is as big as you can get. Okay. So, but we're okay on this point, right? This, maybe I belabored this. It's kind of a technical point, I guess, but I think it's important. Okay. So good. We're all right, right? Good. Okay. So, if we take rho sub a comma c, that's psi, psi, c, however you like to pronounce it. I'll try to say psi so we don't get confused. Okay, if we take this in G, in our preferred mode of writing it, where C takes a value, psi takes a value between 0 and 360, with psi strictly greater than 0. In fact, let's make it positive, so it's not the identity. Okay. Then psi minus k times phi cannot be positive and less than phi for any integer k. This is just by the minimality of phi, that we took phi to be the smallest. Okay? So what this tells us, this implies that we can write C equal to k times phi for some integer k. Okay?
If it's in the group.
Which we assume.
Yeah, okay.
Yeah.
Yeah. Otherwise, then
Right. Yeah. That is a crucial assumption. And further, to express this in the group, what am I saying here? All that means is that rho sub a psi is equal to rho to the k power. Where remember I said rho equal to rho sub a comma the minimum phi. Okay? So this implies any element of G is some power of rho, i.e. G is equal to the group generated by rho, which is just the cyclic group of order n for whatever the order of rho is. For some n. Okay, so if we don't contain any reflections, we get Cn. Now let's go to case 2. Let's assume G contains at least one reflection. Okay, what can we say then? Okay, so first, note that the set of all even isometries of G form a subgroup. Okay,
you talked about,
I'm sorry?
or you talked about before,
Yeah.
Well, that would be the subgroup of even isometries of all isometries. Okay? So now I'm saying if you take some finite group, G, and look at all the even isometries, then that must form a subgroup.
rotations.
Sorry, say that again.
It has to be rotations though, because the transitions can't be in G.
Right. Yeah, so all the even isometries are rotations, right? Because we already ruled out translations being able to be in script G. Okay, so, this is a good, quick homework exercise. Verify this claim. Okay, I'll start you off. The identity is even, right? Because you can take any reflection and square it, and you get the identity. So it's expressible as the product of two reflections. Okay, same type of thing for all the other group axioms. Basic facts about parity. Okay, so then by case 1, this subgroup must be Cn for some And why is that? Well, Zach just said it. That means that this subgroup of G is a finite group that contains only rotations. Right? Since the subgroup of even isometries of G must contain only rotations. We know it has to be Cn for some n. Okay? So now, let's suppose G contains M reflections. Okay, so we're assuming that G contains at least one. And now we're assuming that it contains M. And what we will end up showing is that it actually contains all M of these. Okay? And let's take sigma in G to be one of them. Okay? Then what do we know? Then the n odd isometries. What am I going to write here? Can anybody tell me?
It's the product of sigma with each element of Cn.
Yeah. The n odd isometries, rho sigma, rho squared sigma, rho to the n sigma, where of course rho is the subgroup of even isometries. These n odd isometries are in G. Right? So we know all these are odd because all these rotations must be even. Right? So what does this tell me? This tells me that, oh, I'm sorry. Did I? Yeah, okay, I did. Cn for some n. What this tells me is that n is less than or equal to m. Right? Okay. So now multiply the m odd isometries on the right by sigma. Okay? And what does that give us?
Like the same sigma?
Sorry?
The same sigma?
Yep, same sigma as before. This reflection that we took, that we assumed is in G. If we multiply on the right by sigma, the m odd isometries, then we get m distinct even isometries. Okay? Gives m distinct even isometries. Right? I take all the odd isometries, they're all products of an odd number of reflections. I'm tacking on one more reflection to each of them, so they all become even and they're all distinct.
Because they started distinct, which is.
Because they started distinct, because we assumed we contain m reflections. I guess I should say distinct here. Okay. Okay, so in other words, this tells us that m is less than or equal to n. Right? Because we know that there are n even isometries. There are n distinct even isometries because from case 1 we deduced that the subgroup of even isometries is Cn. Okay? Okay. So therefore, they have n equal to m.
There are no more distinct reflections to add.
And G has 2n elements. Okay? And furthermore, they're all generated by rho and sigma. Okay? So that is to say, this is not any special reflection. I just picked an arbitrary reflection. Any reflection can be a generator of G, this finite group, right? Okay? So, right. Just one last note before we're done, right? If n is equal to 1, well, then we just get G is equal to the group generated by the reflection, or C2. Okay? And if n is greater than 1, then rho sigma must be a reflection in a line through A. In a line through A, and in case you forgot the notation we were using before, A is the center of rho. And that was notation from case 1. So it implies that our group G in this case is equal to Dn. Okay?
All cases.
Yep. Right, so there's only one case when G contains a reflection and it's not a dihedral. It's the case where n is equal to 1. And you just get C2. Okay? So, when you go through it step by step, it doesn't seem... I really like this proof because it uses almost everything that we've done in the past week and a half. And it's just a really nice result.
So how did Leonardo prove it?
I'm sorry?
How did Da Vinci prove it then?
Good question. I haven't seen the original text. I'm not sure. That's
Because he didn't have these tools.
right, yeah. I mean, certainly he understood reflections and rotations, but not in the notation that we've been using. But that would be really interesting to see if you could find that, the original text or any account of the original text. You might even go to Weil's book and see what he says about that. in symmetry, right? Okay, right. So here's a corollary, which again we've discussed, but not in any truly rigorous fashion. The symmetry group of a polygon is either cyclic or dihedral.
Because it has to be finite.
Right, and let's just say a quick justification of why that is. It has to be finite. We already did it for the case of a square. Let's just say it in general here. Okay, so I'll just say sketch of proof. Right. So recall a polygon with m vertices has at most two m symmetries. So it must be finite. Remember this argument we made with the square, where we oriented a square in the plane so it had a vertex on the x-axis. We labeled that v1 and an adjacent vertex v2. So there are 4 possible places for that vertex to go if it's a symmetry. And then for each of those 4 places, there's 2 options for where the adjacent vertex can go. So that same argument applies for an arbitrary polygon.
Because you see what happens when you try to be not finite, you approach the circle.
Yeah, right. Yeah, I meant to look into that a little bit, but I never did the quote infinite dihedral group.
Right.
But yeah, maybe I'll remember to do that over the weekend. In any case, so it's basically that same argument that we made with the square, but just for an arbitrary polygon. Of course, you may well have less than 2m symmetries, right? These are only the regular polygons that have the full 2m symmetries. But in any case, the point is that the number of symmetries you have is bounded. So it has to be Cn or Dn for some n. Okay? Okay. So, a lot of the characterization that we've done of isometries has been in terms of the fixed points of those isometries. Now I just want to take a little time and do a kind of opposite exercise. That is to say, if I take 2 distinct points, can I characterize the isometries that takes one to the other? Okay? Right? We've characterized isometries that fix a certain number of points. But now, if I take a non-fixed point, what can I say are the isometries that do that? Okay, so
There should be a finite number of simplest form isometries that'll do that. Or given a certain.
there's an easy description, a finitistic description, but it's not actually finite.
Interpretations you can just.
It's based on the choice of a line through a particular point, usually. But let's see exactly how that plays out. So here's the question. Given points P, which is not equal to Q, what are all the isometries taking P to Q. Okay. So, again, we'll break into two cases here, namely even and odd, but first we'll set up some notation that we'll use throughout both cases. So, I just want to comment, I know it may have seemed kind of mundane, or perhaps at least kind of laborious, without much payoff, how we've characterized all the isometry, all the ways isometries can be factored and their fixed points and all. But now we're finally getting to a point where it's like, oh, here's the payoff, right? And here's what we can do with all this machinery, okay? And I just want to say that hopefully today we'll get through the first part of chapter 9. And that is a slight detour back into a completely analytic thing, which we'll write down equations, explicit equations for rotations, which if you recall we haven't done yet. And then starting in chapter 10, that's the cornerstone to get to this whole wallpaper result. Okay, so after we get through chapter 9, it's all serious application. Okay? So, just in case you've been bored over the past couple of weeks, hold on. Okay, so in any case, what notation do I want to use here? And it's pretty standard, actually. So let's just let M be the midpoint of the line segment PQ. And little m, the perpendicular bisector. Okay. So, two cases. Let's start with the even isometries that take P to Q. Okay, so, of course, there's two cases, right? There's translations and there's rotations. So, first of all, let's say, remember, one of the first things that we claimed is that tau sub p comma q is the unique translation taking P to Q. Okay, and we may write the following factorization of tau sub p comma q. Right? This is equal to reflection in some line q times reflection in some line m. Right? Where line q is through point q and parallel to m. Right? This is something we've seen time and again, where it's like, okay, we have a translation. How do I construct two lines that I can factor tau in reflections of those lines? I just take two lines that are perpendicular to the bisector of line segment PQ that are half the directed distance, it's half the distance from P to Q away from each other. Right? Exactly what we've done here. Okay, good. So Now, what about the case of a rotation? So let's say if rho sub c comma theta is one of these isometries, takes p to q, I'll just say that. Takes p to q, then point C lies on M. Right? So let me draw you a schematic here, just in case that's not completely clear. And I realized that I was looking through some of the homework problems I didn't assign you, and there was a really good one I should have assigned you, which asks you to prove or disprove that there are an infinite number of rotations that take point P to point Q.
I think I said that.
I did assign that? Maybe I did. But yeah, so just schematically, what are we saying here? Here's our line M. Which is the perpendicular bisector.
I think that was 6 between 10.
Yeah, that sounds right. I'm glad I asked you to do that. Good. Right, so if I pick any point C on this line, then I can rotate P to Q, right? Because any point on M is equidistant from P and Q, meaning that they lie on the same circle centered at C. Okay? Okay. So, then we know there is a line passing through point Q. Passing through C. And we'll show it passing through Q. Okay, passing through C. Call it Q. So that our rotation is equal to sigma sub q times sigma sub m. Okay? Right? This is, I'm just choosing the unique line q that's directed distance from m theta over 2 away. Directed angle measure, not distance. Thank you. Okay? So, note, of course, that we have sigma q, sigma m of p is equal to q, right? Because we assumed that rho sub c comma theta takes p to q, and this is just a different way of writing rho sub c comma theta. But this is also just theta, I'm sorry, sigma sub q of q. Right? Because sigma sub m of p takes p to q also. Okay? So that is to say, q is on line q. That's what I've proven here. Because it's fixed by sigma sub q. And the only points that are fixed by a reflection are points that lie on the axis of the reflection. Okay? intersects M. Why do I say that? Well, I mean, we already knew that, but now we've kind of characterized all the isometries that take P to Q. So let me just say one more thing.
Defined the, that's like we defined it as containing C, right?
Sorry?
That's because we defined it as containing C, that's why it intersects M, right?
Right. Yeah. Passing through C, yeah, exactly. Yeah, so it feels kind of silly to say this again, but it's the same case that we ended up with the translation. That's why I just want to emphasize that's the characterization. Okay. So conversely, if Q is a line through point Q, that intersects M, then we have that sigma Q, sigma M is a rotation taking P to Q, right? That's going the other direction. So now we're done, right? Of course, we didn't have to say anything conversely when we discussed translations because there's a unique translation that takes P to Q, okay? But a bit more subtle when we talk about rotations. In conclusion, and even isometry, taking P to Q, oh, sorry, the even isometries are exactly sigma sub Q times sigma sub M with Q on Q. Okay, so if Q and M intersect, this is a rotation. If they're parallel, it's a translation. Right? Okay. So this is our characterization. Now, how about the odd case? Well, okay. It's kind of a similar dichotomy, right? We have,
Reflections.
right, there's a unique reflection taking P to Q, which is the reflection about the line M, right? So sigma M is the unique reflection taking P to Q. So that takes care of the case of odd isometries that are exactly one reflection. There's only one that takes P to Q. So now we address the glide reflection case, right? Okay. So let's say if gamma is a glide reflection with axis C taking P to Q, then what we know is that M, the midpoint of line segment PQ, is on the axis C.
Right, it's a midpoint.
Right, because it's a midpoint. We actually, yeah, if you go back and look at the first characterization of all the properties that we did of glide reflections, this was one of them. A midpoint lies on the axis. The midpoint of a point and its image under a glide reflection lies on the axis of that glide reflection. That's what I'm referring to here. Okay, right. So, therefore, there is a unique line off M that is not intersecting M, so that, there's a unique line off M, let's call it Q, so that gamma is equal to sigma Q, sigma capital M. Remember, we had this characterization of glide reflections where we can write it as either a half turn followed by a reflection, or vice versa if we wanted. But for our purposes, it's okay to write this, right? Okay. Then, since we have the following computation, Q is equal to gamma of P, right? Our assumption that gamma takes P to Q. Now, changing this to our reflection half-turn factorization. The half-turn about the midpoint of PQ takes P to Q, right? Sigma Q of Q. So again, what we see is, we know Q lies on Q. Little q, right? Because the reflection in little q fixed q, so it has to be on the line q as well. Okay. Hence, a light reflection taking P to Q, has form sigma Q, sigma capital M, where Q sorry, I lost my place. Where Q is a line through Q and off M. Okay, so now, just as in the more complicated case in the the even case, we have the subcase, we have to go in the opposite direction. We have to say conversely, if we have this scenario we get an expression like this, right? Okay, so conversely, if Q is any line through Q and off M, we have sigma Q, sigma M is a line reflection. Line reflection. Taking P to Q. Okay, so now we have a very similar conclusion to the even case, right? But now we have a half term in our factorization instead of just two reflections. Okay, so let me write that down. So the isometries taking P to Q are of the form sigma Q, sigma capital M with with Q through the point Q, right? And I just want to say, what about the first case where I said there's a unique half turn?
M is on Q.
Yeah, rather Q, the line Q is just the unique line through P and Q.
Right, midpoint's on it.
Yeah,
Opposed to when we've had sigma, we had the opposite.
exactly, right.
Just like intersection versus parallel.
Right, so the half-turn case is the degenerate case where your line Q actually hits M. Okay?
Do you mean the reflection case?
Sorry, reflection. Yes, I'm sorry. Since sigma sub M is equal to sigma sub Q, sigma sub capital M, where Q is just equal to the line through P and Q, right? That covers the reflection case that we did first. Okay. Good. So I think that is a pretty nice result as well. That's the end of chapter 8. I'm going to give you just a few homework exercises, not too many. I'll ask you to do 8.7, 8.8, and 8.14. And that'll do, I think.
The first tomorrow, Monday.
Well, I have a feeling like that most people would prefer to review the exam material tomorrow before the exam. But if people have questions about these tomorrow, that's fine. We can address them then as well. But we'll.
And we won't have any new homework tomorrow, so we should have at the beginning of Monday's class anyway for.
Yeah, right. This is just a natural time to assign you homework from chapter 8, but if you, I would completely understand if you were busy studying instead of doing this. I mean, 8.7 might be helpful for practicing for the exam. It's a bunch of true-false questions about the material in chapter 8. So, you know, at least half of them are probably from 8.1. Okay? Okay, so the next 20 minutes, let's take our analytic detour. We're gonna go back
Rotations.
to talking about rotations, and then we will actually culminate our analytic detour with equations for an arbitrary isometry. It's actually, we can write down a nice algebraic expression for an arbitrary isometry, which is somewhat surprising. Okay? So, equations for isometries. Let's start with rotations. Rotations first. Get a fresh marker. It's so nice that the university started putting markers in these boxes again during the pandemic. Instructors had to buy their own supplies. Yeah. Anyway, okay. And in particular, we'll start with the case that our rotations are centered at the origin. Okay, just to make things nice and easy computationally to start. All right. So take rho sub 0, 0, comma theta. Note the change in notation here. Since we're working analytically now, I give an analytic name to my point. That's the center. Okay. So this is equal to sigma m times sigma L, where I arbitrarily choose L to be the x-axis, just because, again, to make things nice to start, where L is the x-axis, and then, of course, M,
Just the line, such as the directed distance.
the directed angle measure will be half of theta. Yep, good. Okay, so I'll just write that down, and M is the line of directed angle measure, theta over 2 degrees from L. Okay, so, sorry.
Any origins on that also.
Yeah, through the origin. Through 0, 0. Good. Alright, so L, M, theta over 2. Okay. So, by the definition of trig functions, we know that the point cosine of theta over 2, comma, sine of theta over 2 lies on M. Right? That's when you first introduce trigonometric functions, it's the x-coordinate and the y-coordinate of some line that's an angle off the x-axis, right? That's usually the way people first see it. If I'm wrong about that,
Using a circle, but yeah.
Yeah, right. Maybe you saw it on the inner circle first. Okay. So what does this mean? Well, this implies M has the equation y equals sine of theta over 2 divided by cosine of theta over 2 x. Right? Because we insisted, of course, that M go through the origin. So its y-intercept is 0. Okay? And in case it was mysterious where I pulled the slope of a line through the origin is the tangent of the angle, here you go again. And so I was hoping that we got to this point today, especially after we had some questions about that problem on the practice exam. So good. Okay. So, which of course we can rewrite this in standard form, right? Which is what we usually want to do. Look back, for example, at the equations of a reflection, right? We use the standard form of a line to produce the equation for a reflection. Okay, so this is the same as saying we have sine of theta over 2x minus cosine of theta over 2y plus 0 equals 0. I just put the 0 in just to make it completely transparent what we're doing when we put it in standard form. Our c is equal to 0. Okay, so now remember I wrote this rotation that I started with as the product of two reflections. And I know the formula for a reflection given the equation of a line. So that's what we're going to do now. We'll write the explicit equation for reflection in M using this formula for the line M. Okay? Warning. Trigonometric identities ahead. And you're not going to have to know trig identities, but you should still see this commutation. Okay? All right, so what's the formula for a reflection? Well, for the first coordinate, we get x minus 2a, which is sine of theta over 2, times the whole equation of the line, right? Sine of theta over 2 x minus cosine of theta over 2 y all over a squared plus b squared. Okay, so sine squared theta over 2 negative cosine squared is just cosine squared.
Well, that's nice.
Yeah, it's not as bad as it might seem at first glance. Okay, and then I'll write my second coordinate a little lower just because I don't have enough room to put that here. Y, our second coordinate is 2b, which is just 2 negative cosine, sorry. No.
So it should be positive and it's by plus then?
Yeah. So I'll just take that a plus. Good. Okay, so times, again, the equation of our line. All over sine squared of theta over 2 plus cosine squared of theta over 2. Okay, so first of all, sine squared plus cosine squared is 1, no matter, as long as I have the same argument. Okay? So, let me rewrite this in yet another form. Right? So, I can exclude these denominators, they're just one. And now let me just distribute the outer terms. Right? So, x minus 2 sine squared of theta over 2 plus 2 sine theta over 2 cosine theta over 2. Yeah, most of these things end up being identities that we get here. Comma, y plus,
Are you using the X and Y there?
yeah, totally. But I got ahead of myself there. Sorry. Okay, right. So, yeah. I have an x here and a y here. Yeah. Good. Comma. Y plus 2 cosine theta over 2 sine theta over 2 x minus 2 cosine squared theta over 2 y. Okay? All right. So basically, if you look up all the double angle formulas, so I'll write this. Double angle Mac gives you that this is all equal to the first coordinate is cosine, I don't want to put that many parentheses in. So, cosine theta x plus sine theta y, comma.
This is including our first coordinate.
Sorry?
It also includes our original x.
This is our original x. This is our original input.
Yeah. Okay. No, I mean like the identities absorb the original.
Oh yeah. Right. We factor an x here.
Yeah.
Right. So yeah, I didn't do all the steps to get to the double angle formulas, but write this down and do the trigonometry yourself if you like. I just felt like that wouldn't be that useful to us because we're not going to use it after we derive this formula. Okay. Right. So and our second coordinate is sine theta x minus cosine theta y. Okay, so quite the mess, but it turns out not so bad, right? Okay, well, great. So now all we have to do to write our original rotation centered at the origin in an explicit formula is write the formula for sigma sub L. What was L? It's the x-axis. That's an easy formula, right? We just negate the second coordinate. Okay. And, of course, sigma sub L of x comma y is just x comma negative y. Okay? So, we've shown shown. In the plane, rho sub 0, comma 0, comma theta has equation cosine theta x minus sine theta y, comma sine,
Why is that negative?
because y.
Oh, yeah, why is it negative? Okay.
Yeah, because we applied L, sigma L first.
Okay.
Yeah.
That's why the rotation matrix is cosine negative sine.
Yes.
Sine cosine.
Exactly. Great observation. And we won't actually get to talk about the matrix form of this, but that's exactly why. You're right. Okay, so sine theta x plus cosine theta y. Okay. So that's all well and good. This is not so bad, right? But it's somewhat limited, right? Because I have a fixed center here. What do I do to get at a rotation that has an arbitrary center?
Can you translate the center to the origin, form the rotation, then translate back?
Yeah, exactly, i.e. conjugate,
Yeah.
right? We multiply by the translation. Okay, say we have some center hk, and we started with an equation for a rotation around about the origin.
Negative h negative k.
Right,
Or the inverse of hk.
right, so actually the translation is if you switch the order of origin and hk, right? So, yeah, there's just a little bit more to say about these matters, and we'll just do that first thing on Monday, and then we'll start chapter 10. Great, so don't forget about office hours this afternoon and tomorrow morning if you want to ask any additional questions. And yeah, oh yeah, I guess I should announce that tomorrow after class, or rather after you're done taking the test, I'll send out practice tests for test 4, which is at the end of the following week.
It's not next week, the one after.
Next week.
Next week.
Oh,
Next week.
It is next week.
Yeah. Yeah. So I think I will send out a survey. Depending on what people want to do, we're still a little behind. So we could push back the exam to be in the middle of the week after next. That makes it kind of much closer to the final, but you'll have more time to prepare. I'll send a survey out, and just know that might get pushed back, depending on what you all want.